Hi everybody, welcome to another video. We'll do the announcement and everything later, but I wanted to kind of add this to the beginning even though I'm all done with the whole project. And the reason is, if you get a chance, I would like you to go check out Manuel over on Electronics Old and New by M. Caldera, I think is the name of the YouTube channel. He just released a video on aligning an old vacuum tube style FM tuner, and he did a fantastic job. He put a lot of time and hard work into it. He erased all of the non-relevant circuitry on the schematic digitally so that you see a real clear view of just the FM station. He shows a method for a non-visual alignment of the receiver using a couple of 100K resistors, and lo and behold, if you look, that's the same procedure that we use on this one. I didn't do it on this particular video. I did do this. I have somewhere, I don't know. It's kind of a similar jig that I use, but anyway, the alignment was pretty spot on this thing. I didn't really have to mess with it a whole lot. But anyway, check out his video. It's a good precursor to this one, because if you watch that first, you'll get a good idea of how FM alignment works. And then I get into pretty good detail in this video on how the multiplex works and the whole concept of subcarriers and so forth. So between the two, hopefully it'll help you get a better understanding of how FM stereo works. All right, let's get on with the video. Hi everybody, and welcome back. So today what we're going to do is, this is going to be our final part in our H.H. Scott 399 video. We're going to end it up by hopefully getting this LM35 wideband stereo multiplex adapter to work. The purpose of this little module is to take the mono receivers that we have, like the Scott 399, and add stereo multiplex to it. So it's going to allow the H.H. Scott 399 to receive FM stereo multiplex signals. Now, this isn't a tuner in and of itself. This is a demultiplexing device. It's something that will sense the stereo signal that's already present in that FM radio station. It will decode it into left and right channels and then feed it into the amplifier. But the tuner in the Scott 399 is what will actually receive the radio station. Nothing changes there. The only thing this does is this takes that, the tuner built into the 399 can only see a mono signal. It will only see part of the broadcast on that carrier. This allows you to see the whole broadcast with right and left channel data. So hopefully that makes a little bit of sense. We'll get a little bit more into theory how FM multiplex works. I know I've done that in a previous video, but we'll do a review of it. And then we'll look at the schematics to see kind of what this is doing. And then we'll try to see if this, I'll check it very quickly. This was a kit. You can see it says Scott kit. Somebody built this from a kit. So we don't know if it ever worked, or if it does work, or if it doesn't work, or we don't know anything. So I'm going to just do a peek inside before we plug it in. And we'll also look at the schematic. So if that sounds interesting, stay tuned. To understand how stereo works, we have to first understand some of the problems or challenges that it poses to us. In front of you, I just have a digital audio player, and this just represents a music source. So this could be a record player, this could be a tape deck, this could be your digital audio player like this, your cell phone, anything that has an output, an audio output. And as you can see here, you have two channels, right and left. And of course you would take your patch cords and you would plug into here, and then you'd plug the other end into your amplifier. And your amplifier is, if it's stereo, actually has two amplifiers in one, right? You have your left channel and your right channel. So you have a left channel and right channel audio source, left channel and right channel amplifier, and left and right speakers or headphones. So you have two distinct audio sources, the left channel and the right channel. Think about that for a second. What we're looking at right here is a carrier signal from my HP 8657 signal generator. If you look at the frequency, it's around 99.5 megahertz. And the amplitude is, I cranked it up pretty high for a radio signal. But this is what a radio signal looks like. It's just a single sine wave that can be changed in order to deliver sound and data. So whenever we change the signal in any way back and forth, we refer to that as modulation, or modulating the signal. So if I were to take this signal and it's sitting at, let's say, 590 millivolts is its peak amplitude, and if I varied it up and down, for instance 100 times per second, I would be amplitude modulating this carrier signal. We call this the carrier, the main radio signal. I would be amplitude modulating it at 100 hertz. And of course that 100 hertz is a sound that's in our hearing range, right? We could hear that. If I varied the frequency from that 99.5 back and forth 100 times per second, once again, I would be frequency modulating that signal at 100 hertz. A radio will take that signal and it will erase this radio signal and only leave behind the modulation, whether it's AM or FM, depending on what you do. So if we turn on modulation, you see how stretched those get? And if I shrink this down, or if I close up this waveform, we will begin to see something here. And I may have to turn it down a little bit. And you can see there is your modulation. Now, if we wanted to count that, it should be around 400 hertz. Now, the frequency counter's going crazy because you have all kinds of frequencies in there. But this portion right here is 400 hertz because we're putting a 400 hertz amplitude modulated signal on there. Now let's go back out to the looking at the radio signal again, right? I'm going to turn off the modulation, and you can see it once again looks like a regular signal. And if I turn on FM modulation, you don't see very much, do you? Because that signal is moving so quickly and such a little bit, you don't really notice it. And no matter how much I increase this, I don't think we'll be able to see it. But what's happening is the frequency is varying ever so slightly. The problem is I can only put one modulation signal in there. In other words, whatever goes on here is going to be a single carrier with a single signal. And therefore, if you remember, we have two signals, left and right. How do we tell this one carrier which one is the left signal and which one is the right? You would need two different carriers, wouldn't you? Maybe. Well, some folks back in the 1950s and 60s came up with some pretty good ideas of how to work around this. And that's what we're going to learn, how to put two channels into one single carrier. And that's what we refer to as multiplexing. Let's look at it. Now, to put these two channels onto one single carrier, we have to prepare it. And there's a few tricks we're going to use, and one of the terms that we're going to hear about is called a subcarrier. A subcarrier is just what the name implies. It's a carrier that rides on top of another carrier. So your main carrier is always going to be a higher frequency. For instance, your RF frequency on FM would be 88 megahertz up to 108 megahertz, right? And the subcarrier is going to be a lower frequency than that. Before we look at the actual circuit and the waveforms, let's just do a brief overview of what multiplex stereo is. I did videos on this in the past, so we're just going to go over it real quick. First thing you need to know is with FM broadcast radio, the radio stations are spaced 200 kilohertz apart from one another. So every 200 kilohertz you have another FM station. So you can go 100 kilohertz in either direction, and you'll have a 200 kilohertz spread. That's called deviation for your FM modulation. And if you go any more than 100 kilohertz, like in this direction or this direction, you'll actually overlap the deviation range of the adjacent station. Now, when they designed this, they thought that that was so much bandwidth because really they're limiting all of the audio to only 15 kilohertz. So you have tons of extra space in there. And the original reasoning behind that was that they were going to do a secondary carrier all along, and they did. And what you could do is you could actually broadcast one carrier or one station and have multiple audio tracks on it by using secondary carriers. What they did not plan originally was stereo sound. So the original plan, you would have your first, your main channel, which is your main FM station, and then they would do a secondary or an SCA carrier right next to it with another hidden channel, and that would be like that elevator music you hear, background music. That was like a paid subscription type thing. You had to have a special receiver to pick it up, all that. And when FM stereo came out, they actually had to move that. So if you look, it's over here now. So anyway, this is kind of a little breakdown. Now what you're looking at on here is a pictorial representation of all of the sound information that's being packaged together into one package and modulated while keeping it within that plus or minus 100 kilohertz band limit. Now, each one of these is in a different colored box. Do you notice that? So there's the dark red, the light red, the green, there's this little purple looking line, and then there's the blue. And each one of these is its own separate, independent signal. And what we're doing here is we are combining each of these signals together. So we're kind of mixing them together, just like if you took a mixing board, when you in the recording studio and you take the different sounds, you mix them all together, and all of those sounds come together and they come out your speaker as one complex sound, all the sounds all together. And that's what this is. And in the process of mixing all these signals and combining these signals is called multiplexing. That's where the word multiplex stereo comes from. So this dark red area, if you notice, it's low frequency. It's in the audio spectrum where you can hear with your ears. And it's between 0 and 15 kilohertz. So any of the sound that you hear with your ears will be in here, and it's capped off at 15 kilohertz. So really FM radio does not have the capability of covering the entire healthy ear hearing spectrum. Now this more than adequately covers my hearing spectrum because my ears drop off pretty abruptly after 12 or 13 kilohertz. But anyway, this is your left and right audio mono mixed together, and it's just one single transmission. And if you're transmitting on a mono FM station, this is all that you would see. You would just see this portion right here, nothing else. This is all they transmit. The rest of this is not necessary. But in order to transmit stereo information, you need some other information in order to be able to regenerate or unpackage the left and right from one another from this signal here. In order to do that, they used a pretty elegant method. They took the right and left once again, and instead of adding them, they subtracted them. So you take the left channel and you subtract the right channel from it. And by doing that, you're going to get, first of all, you're going to get about half, if both channels are playing at about the same amplitude, the same volume, what's going to happen is you notice this signal is going to be about half the amplitude of this signal. But that's okay. We're going to find out why in a minute. The other thing we're going to do is we have to be able to keep this thing in phase with this signal. They need to be in phase with one another, or when we demodulate them, they'll be all out of phase and you'll get all kinds of harmonics and weird sounds. And so it's important that we have some way of doing that. And that's what this little 19 kilohertz signal is. So the next thing we're going to transmit and add to our little mixer is a 19 kilohertz pilot tone. This is only going to be about 10% of the amplitude of the rest of it. But what it is going to do is it's going to keep the phase relationship between all of these together. It's also going to be very significant. This number one, it's above where we're filtering off all the sounds. In a mono tuner, you're filtering out everything above this 15 kilohertz. So at 19 kilohertz, this isn't going to be ignored from a mono tuner, but a stereo tuner will pick this up above your left plus right sound. Now, another thing we're going to do is we're going to do this left minus right, but it has to be a little bit different. If we were to just transmit this as another signal, we first have to shift that audio. Remember, this audio is also 0 to 15 kilohertz, but this part of the band is already being occupied by the left plus right. So we just want to take that audio signal and shift it up here. In order to do that, we're going to take this 19 kilohertz and double it to 38 kilohertz. That gives us plenty of space to have 15 kilohertz here and 15 kilohertz here, plus and minus. Remember, this is a amplitude modulated signal at first. And these two side bands are where your audio is going to reside on either side. On the positive side of 38 kilohertz and the negative side. Now, why in the heck would you do it this way? Well, first of all, let's say that there is no channel difference going on. Let's say there's no audio at all. Let's say that you're just playing radio silence. If we had a regular carrier signal sitting here, running all the time to just make sure that shifted signal is always sitting there, your transmitter would be transmitting full power another carrier signal. So it'd be almost, it would be sucking up all of your bandwidth just to transmit silence. So what they did is pretty brilliant. They block the 38 kilohertz carrier wave, and then they allow the two sidebands to come through. That's called double sideband with suppressed carrier, or DSBSC. So you see this is in blue because it's suppressed. In other words, the transmitter never sees this. It's just sitting there. All it's going to see is whenever there's sound, it's going to have these two signals here. And when we take these sidebands and we combine them mathematically with the left plus right, you're going to get this. If you take the left plus right and you add the left minus right signal, this one right here, you're going to be left with 2 left, or the left channel at double the amplitude of this, which is going to be the same amplitude as left plus right, correct? So the volume level will be the same. If you take the left plus right and you subtract left minus right, okay, these guys will cancel out and you get 2 right. Because if you subtract a negative number, it's like adding it. And of course that 2 right will be double the amplitude of this, which will be the same amplitude as this. So now we have a left channel and a right channel. Pretty brilliant, huh? And when there's no sound being transmitted, you're not using up any energy on your transmitter. So you're not overheating your transmitter. Pretty cool. Now these guys above here have all been shifted up, and it works the same way. We have another carrier, and this is called the secondary carrier. And this is used for the, again, for the secondary, the background music channels, as they call it, and so forth. Anything like that can still be up here, and we're still cutting it off at about 74.5 kilohertz, so we're way far away from that 100 kilohertz cutoff point. So we don't have any chance of overspilling into another adjacent channel. So look at how much information we get in that one little space by using multiplexing. This here, this at 57 kilohertz, crammed in between the 53 and the 59.5, we have the radio data system. And that's, you ever see your modern radio when you turn it on, like in a car radio? It can actually tell you the station information a little bit, the name of the song, the channel, you know, information and so forth. That's from this. It's very narrow bandwidth, but just enough to broadcast little text messages. And that's stuffed in there. Now, when we're talking with HD or digital radio, this has changed now. It's not the same. This is old analog multiplex that we're talking about. Okay, so don't get confused with that. This is traditional FM multiplex. That's how it works. If we take all of these individual pieces and we mix them together in a mixer, we have what's called a composite multiplex signal. The radio or your multiplex unit in your stereo is going to disassemble all of this and turn it into that 2L and 2R. And that's what we're going to look at next. Right now, whether you know it or not, I actually have part of the multiplex signal going into this oscilloscope. And as you can see, it's a totally flat line. And the reason it's a flat line is because part of what we have to do is we have to suppress that 38 kilohertz carrier tone, the center of it. The reason being is if that 38 kilohertz was sitting there all the time, your transmitter would be transmitting a lot of power all the time when it's not necessary. In other words, it's transmitting signals that it doesn't need. In other words, if there's no music playing, if there's no sound, there's no reason to be using up energy on your transmitter. And this is exactly how single sideband works. If you notice on a single sideband, you won't see a carrier signal on those either. A single sideband only has a carrier while it's modulating, and that's exactly what this is. But this has an upper and a lower sideband. It keeps both sidebands, so this is called double sideband suppressed carrier. That's what we refer to it as. And really, simply all it means is you don't see the carrier until you start putting modulation on it. Now, I'm going to add, before I add the modulation, I'm going to add that pilot signal. So let's put the pilot in there. And you can see there is the 19 kilohertz, and it even says 19 kilohertz. And this is kind of gritty on the LCD screen here. Let's move over to the other scope for a minute. It's just a little easier to see on this, a little sharper. Here we go. And you can see there is our 19 kilohertz. And I can change the amplitude, but that's the 19 kilohertz. Now watch what happens when we add some signal data, left and right channel. Looks like a giant mess, doesn't it? Pretty strange. And it's all flickery and kind of hard to see, right? But what you're actually seeing right now is, now that there is left and right channel data, and I'll explain why it looks like this in a minute. Now that we have left and right channel data, you're actually seeing the pilot tone and the modulation, and the carrier, the suppressed carrier, is kind of all one big clump now. Now let's just look at one channel at a time and see if we can figure out what it is. I'm first going to turn off the right channel. And you can see there we have an actual frequency riding on it. See your sine wave? And this would be your left channel because I turned the right channel off. So now this modulation circuit is only showing one side of it. So the right channel is not adding into there, so now you just see the left channel riding on the carriers. Now if I go to the other one, turn it back on, turn the left channel off, it looks different, doesn't it? Well, there's a reason. Let's look up at the signal generator. Channel 1 is the left channel, channel 2 is the right channel, and if you notice, left channel I have 400 hertz, right channel I have 1 kilohertz. See that? So I actually have two different tones being modulated at the same time. 1 kilohertz on the right and 400 hertz on the left, and when you combine them into a mono signal, you see a complex waveform of those two frequencies mixing together. So here, let's turn them both on. That's what that is. That's a complex waveform of both right and left channel together. Whereas if you look at the left channel, which is your 400 hertz, you see a longer period of time. This is actually 400 hertz. And if I look at just the right channel, they're closer together because it's a higher frequency. It's 1 kilohertz. That's exactly what you're seeing in a multiplex stereo composite signal. This is called a composite multiplex signal. In other words, all of that information is in one package, and that one package now just needs to be modulated onto the main carrier to be delivered to your receiver. That's what we're doing. Now, our multiplex unit is going to do just the opposite. It's going to strip all of that information. It's going to look at this frequency, and it's going to look at this frequency, and it's going to remove all of the carriers from it and only leave behind the frequency data. So that's how this works. Let's look at the schematic now, because I think this multiplex unit is probably one of the most simple layouts or simplified designs of this you could get, and it's very easy to see how this all works. Let's look at the schematic. And yes, a digital scope will display this as well, but I just don't like the way it looks, it appears, as much as I do on the older analog scope. It's just a personal preference, but you can still use your digital scope. It won't hurt anything. There's no problem. And if I look at the individual, it's there. A little bit harder to trigger sometimes, and you can play around with the trigger settings, but it works. When you move it over to the other one, it's a little bit easier for me. The buttons are quicker to work with, and it locks in much better. And you can look at the different. So there you go. Here's the schematic of the LM35 stereo multiplex adapter. And remember, this is not a radio receiver. All this is something that will take that multiplexed signal once it's received by a tuner and break it apart into right and left channel again. So you can see right here, multiplex input. This is where you're going to come off of the IF circuit of your FM tuner. And the FM tuner is going to be tuned into the stereo station that you want to listen to. And when it comes in here, it's already going to be demodulated in the point that the main carrier will be taken away from it. So that's going to get buffered through a little amplifier. And the first thing this thing wants to do is it's going to take some of that signal and run it down through here, and it's going to run it into this 19 kilohertz amp. And what this is doing is this is where it's going to pick off the pilot. In other words, this is going to filter out all of the sound data, the left and right and so forth, and only leave the 19 kilohertz tone, the pilot tone. It's going to amplify it through this little pentode tube here, and then it is going to send it into this little circuit here, which all it does is it doubles that 19 kilohertz tone into a 38 kilohertz tone. So it's going to restore that suppressed carrier. It's going to need this information in order to extract the left plus right from the left minus right. So then it's going to do that. That goes up into here. The rest of the signal goes through this little leg up here and goes into a detector circuit, which is simply just some diodes. And these are actually 1N294s, which I believe those are germanium diodes. Don't quote me on it, but I'm pretty sure they are. And what these are going to do is this is the actual part here that's going to take the left and right and split them apart into left and right signals. And they're going to do it by the phase relationship between each of these sides and that 38 kilohertz signal that you're putting on here. Once it does that, you're going to strip that 38 kilohertz and filter it out once again, and the only thing that's going to be left is going to be your right and left channel information, which gets amplified again a little bit, and then you have your left and right output. That's how it works. Now, I'm sure I skipped over some things or misspoke on some things, but you radio guys who probably know a lot more than me, feel free to chime in anytime down in the comments section. But what we're going to do right now is, now that we have an understanding of how it's supposed to work, now let's check and see if it works. We're going to take this thing apart and just kind of do a little inspection, and then we're going to put power to it and see if we can undo what our multiplex circuit has done, or our multiplex generator has done, let's say. Okay, skipping ahead a little bit, I took all but this last screw out. And let's see what kind of build job they did on this. Wow. Can you tell that this was a kit? Obviously, the person that built this knew what they were doing. It's a fairly nice job here. The soldering is pretty good. And of course, this portion is factory built. The only part that the kit involves was this back part here, the power supply. You wired that. and then the front part, the switches and the coupling between the main module and that. But all this was factory done. But looking up here at the parts that were done by the hobbyist, certainly did a good job. And I don't see anything burned up. I don't see anything that looks out of the ordinary. And I don't see anything that doesn't look safe to try out. So let's bring this up on a dim bulb. And I'm going to put the cover on so I can flip it back around. I definitely want it to be shielded so we don't have any noise. So we'll put the cover back on and let's flip it. We'll flip it back over and power it up. Hopefully we have everything in frame here. Up here's our voltmeter and down here is our dim bulb. I just have this one little 40-watt bulb in the circuit right now, and let's see. Let's turn it on. Very nice. 160 milliamps and dropping. Wow. Okay. Let's look over at the tubes. We'll see if they are glowing. I can see from here. I don't know if the camera can pick that up or not, but we definitely have light on the tubes. That's a good sign. Turn that off. There, we can see the tubes glowing now. I don't know. Do we dare? Do we dare to connect a signal to this? Let's see what it does. Okay, here's the scenario. I have the audio generator with left and right channel, and we have 400 hertz on the left, 1 kilohertz on the right. Those wires come out of here and they go over to the input of the SG80, and we're using this as a multiplex generator right now. I then am coming out of the output of the generator, and one wire goes around to our scope so we can still see our multiplexed signal with left and right on it. And the other wire right here goes down to our multiplex unit right there. And we have left and right audio output, and those come out and go up to the other oscilloscope. And lo and behold, when I hooked it up, it worked. Look at that. I haven't touched anything yet. Now you can see our 400 hertz is on the left, our 1 kilohertz is on the right. Wee little bit of distortion on the bottom part of the waveform. Nothing too terrible. And if I shut off left, see it goes flatline. And if I shut off right, it goes flatline. So it works. And just so you know, that's with the left or with the right signal with 1 kilohertz, and that represents this. And if we go to left only, and it's not, the trigger's not triggering on that, it's not syncing on that, that's why it's scrolling like that, but that's okay. That's just the scope, I could change it. And over here, there's our 400 hertz. So it works. I hope that gives you a more visual understanding of what's going on in stereo. Now let's now that we know this thing works, let's flip it back over and see if we can see some of the signals as they're working in the circuit. So let's start out. We have our composite signal coming in here. It goes through this little amplifier, and then it branches off down into our doubler circuit and our 19 kilohertz pilot circuit. So let's look right here at this point, and we should just see an amplified version of our composite signal. So here's the 1 microfarad capacitor. There it is in the circuit. You can see we have the scope connected to it. And when we look, right there is our composite signal. Very good. All right, now let's take our scope probe and let's move over to our output of our drive circuit right here, of our, I'm sorry, our 19 kilohertz pilot signal. Let's check it right in here. So that's going to be the output of this little coil down here. So let me move over to that. Let's see where we are here. You can see what I'm doing. I think this is it. We'll know in a minute. And we have a big messy signal now, don't we? So let's check it out. And that doesn't look very good, does it? Well, let's turn off the left and right audio. And let's expand the time a little bit. And as you can see, that's a 19 kilohertz signal. Now, of course, when you add modulation, it stays on that 19 kilohertz. There it is. See it amplitude modulating it, left and right channel? But if we take that off, you just have your 19 kilohertz pilot. Okay. From there, it goes into this doubler. Now, this is not a doubler like you think, because each one of these is still going to be 19 kilohertz, but they're going to be out of phase. And I'll show you what I'm talking about. I'm going to take one scope probe, the one that we've been using, and I'm going to connect it to the one output of the one side of the tube. Okay, so that would be, for instance, pin 6, which would be the anode of the first half of that dual triode. I'm going to take a channel 2 probe, and I'm going to connect it to the other side. And then I'm going to go up here and I'm going to turn channel 2 on. Let's see here if we can do this. I'm going to chop it. Channel 2 on. And as you can see, there's our 19 kilohertz again. But if you notice, they're 180 degrees out of phase from one another, right? They're inverted. And if I take this one and I put it on top of this one and I add these two together, you can see I get double the pulses and I have my 38 kilohertz. So that's what's happening there. Now once again, when I turn on my audio, it's going to ride on there and you see it jiggling around. We turn it off, cleans back up, and you're seeing a little bit of noise now because I have all the test equipment in there and everything. But that's what's going on. Now, from there, that mixed signal goes up here and it's going to get detected on each side. So you're going to detect the upper half of the waveform and the lower half of the waveform, and you're going to break them down into right and left channel data. So let's look at that. So we're going to go, it comes out of this, and the one side goes around here and into this side, and the other one goes around and into this side of the detector, and then it's going to come out as right and left channel. So let's go look at that. We'll go look right here at the inputs of these matrix amplifiers. Okay, we now have the scope connected to the outputs of these 12AU7s because this is a really tiny signal on here. So we're looking at the outputs of these. And if you look up here, it looks kind of like that. It's very messy looking, isn't it? So our 400 hertz is right here, and you can kind of make it out, see it? And our 1 kilohertz is right here. Now the scope's having a really tough time with this. This is hard to lock onto with all these noisy signals. Now what's going to happen is, the reason you're seeing all this garbage is you still have your carrier signals attached to our audio signals. even though they've been detected, the carrier is still there. So now what we want to do is we want to get rid of that carrier again, and that's what these little filters are going to do. And if we go back over to the outputs here, which is our AF, on the other side of these filters, you're going to see a clean output. So let's do that. We're now connected to the output of the audio after it's been filtered. And sure enough, there's your output. Your 401 kilohertz. And that's exactly what's happening inside a multiplex circuit. A couple of things worthy of note here. First of all, you will see that there's a stereo light on here. That is not a normal stereo indicator that you would see on a normal stereo receiver. This light normally would be connected to what's called a pilot detect circuit. So it would be a little circuit that comes off of here, and when it detects that 19 kilohertz being present in this area, it will actually turn on either a little tube or a little relay or a little transistor or something that will illuminate the light to tell it that it's in stereo mode. Also, in even more complex systems, it will enable or disable the whole stereo circuit itself. So it'll bypass the whole multiplex if there is no stereo pilot signal, 19 kilohertz pilot signal present. Of course, none of that exists in this. As long as this thing, all this light is, if you look here, here it is, you can see your 150 volts that's on your power indicator. When you rotate this into stereo mode, it just turns this on and turns this bulb on. So really, all this is a light that's connected to this stereo switch down here. And I don't know if the lighting will, if I get in here a little closer, you might be able to see it. There you go. So that's actually connected to this bulb. So really, this is not a stereo station indicator. It just tells you that you have the unit turned on and enabled. That's one of the things. This is an old-fashioned system. It's everything you need to decode a modern multiplex signal, but none of the bells and whistles you'll see on the newer receivers. Now, this method of detecting the pilot, doubling the pilot signal, and then running it through a detection circuit to demodulate it and splitting it, that's a relatively old way of doing things. And I think you've seen on some of my other videos some of the new ways that are done it with phase lock loop, where they'll actually take that 19 kilohertz and they'll lock onto the phase of that 19 kilohertz, and then they'll use a PLL circuit to keep everything in line. And what happens is all of these frequencies, there is no drift. In other words, all these little components, the tubes, the capacitors, the resistors, all the outside noise, all those things can affect the circuit and can make these frequencies drift ever so slightly, which can add distortion or reduce sensitivity, for instance. Whereas when you use a new modern phase locked circuit, it keeps all those frequencies locked right on to their correct frequency. Then you have synthesized frequencies. There's all kinds of different things that you can get into. And for instance, like the Pioneer and Marantz and Sansui receivers that we work on, all of this whole circuit is one tiny little 8-pin chip, an integrated circuit, including the phase lock loop, everything. It's all in one chip. You can do it all with a chip now. So this is the original old way of doing it, but understand that the principle behind this, if you understand how this works, it's much easier to learn how the more modern or more complicated types of multiplex circuits work. They all do the same thing. They split that left and right into an individual left and right signal, and they may have some different methods of approaching it, but in the end, that goes into signal is the same and the goes out of signal is the same, just a little bit different circuitry going on in between. Well, let's do what I've been waiting for a very long time now. Let's bring the Scott 399 back onto the bench, couple it up with this, and feed it a real stereo signal and see how it sounds. I thought I'd show you the connections for this because it can be really confusing, and if you don't have the original owner's manual for this, which I do not, it makes it difficult to connect this thing. So first thing I'll show you is, it's kind of a blurry image. I zoomed in on it a little bit from the instructions. If you have the assembly instructions for the LM35, there is a little blurb in there how to connect a Model 399. And if you notice, here's the back of the 399. You're going to connect your audio right and left channels here and here. There's like a RCA jack that's sticking out on its own. This is a special connector. It has this little pinch tab on the back, and when you push the center pin of the RCA jack, it pulls it apart. And one side has a little piece of like fish paper on it, and the other side is a metal contact. It separates the contacts, and what it does is these two connectors are connected together through that little internal switch. Pushing this in there pushes those apart, and then it kind of creates a loop. And they're very, very flimsy, and this one is just completely worn out. And that's this connector right here, this red wire right here. And you can see if you push in on this connector, it just wants to push it right back out. It is connected, but it's not very tight. So that might be something, if you have a problem with this, that might be a place to check. The left channel then would connect right here. I'm sorry, yeah, put the right side up. Where was I? Yeah, it would connect right here. So the other thing is the multiplex signal is an unmarked connector on the top, right up here on the top of the Scott 399. So if we look over here, that's where that is, right here, right next to the power transformer. That's your multiplex output. It comes out and it feeds into the multiplex input of the LM35. Your right and left channel audio output come out of here, and they patch in to these two connectors, this one here that I told you about, and this one right here. So that's kind of the way the loop goes. Now these two right here that you see, I am actually in the wrong connectors. It's got to be back here. These ones are the record jacks. They're the outputs, and they're going to go up to my audio interface that's behind this light. You can see it up there. And I'm going to record the music on Audacity through my audio interface. If this all works, I'll be pretty amazed. But we do know this is working because we just checked it. So let's see now if we can actually receive the multiplex signal, strip the multiplex off of it in this tuner, pass that signal to here, and then turn it into audio and put it back in here to the amplifier. If it works, we'll all be happy.
Front, center, side, left, side, right, front, center, side, left, side, right.
All right, you're going to have to look at the pizza I spilled on my shirt. Well, I hope this sounded good to you. I haven't even listened to the recording yet. I can tell you on the speakers, it's dead silent. There's no hum, there's no background noise, no hiss. So anything that the recording picks up is something coming out of the record jacks or with the wiring or something in the recording. But who knows, maybe it'll turn out real good. The stereo imaging is very good. I put a little left-right demo at the beginning, so hopefully you got to hear that. And here's the setup, you got to see it. So we're all done. Our project is finished. So again, I want to wish you all peace, joy, happiness, and good health in your lives. I'm going to get this wrapped up. Maybe one of these days I'll build a case for this. It really could use one. This sits a little bit above this antenna, but if you build the case the right way, that's not going to matter because there should be a cutout here to let all the power tubes in the back vent their heat out. So we'll see. We'll see. Maybe we'll do a shop video when the weather clears up a little bit and I get a little more time. Anyway, we'll see you again real soon. This was a fun project, and I hope you sure enjoyed it. I know I sure did. And until next time, take care. Bye-bye.